Before we get started today, let's take a brief moment to make sure we understand where we're at. First of all, the derivative, something like y prime or dy dt, is a measurement of how something is changing. It's a rate of change, and it's telling us either how a function is changing right then or how a variable is changing over time, but it's a measurement of change. We also learned when we did implicit differentiation that if you have a relationship like y squared plus x squared equals 7, and you do the derivative on both sides, we can end up with something like 2y prime, and solve for y prime. And then we said, well, what if we do the derivative with respect to time? This was last class. We said, well, if you do the derivative with respect to time and you have a relationship between two or more variables, what will happen is we'll get a relationship between their rates. And what that is how are those variables changing over time? And so we could take any relationship between two variables and change it into a relationship between their rates. We call this related rates. Today, what we're going to be looking at is like, well, what are a lot more situations where we have a relationship between two variables, so something like this, and what does that tell us about their rates? And today we're going to be focusing on some geometrical related rates. So this is what happens when you have the relationship between two variables, and you want to know how does it affect one when the other one changes. So for instance, maybe we have a circle, and we know there is a relationship between the radius and the area of the circle. And so what happens is we know that like area equals pi r squared. And we know that if the radius changes, the area will change. That's from before calculus. Okay. So if we have a bigger radius, we will have more area. If we have a smaller radius, we'll have less area. We know that. Now the question becomes like, well, if the radius is changing, so if for some reason the radius of a circle is changing by a certain amount, how will the area be changing? Or if the area is changing, how does the radius change? So that's an example. Another one might be like a triangle. What if you have a triangle? Well, we might know the relationship between the sides, like maybe it's a squared plus b squared equals c squared. And we know that if a goes up, then c will go up. But the question is, if you're moving one of the sides at a constant rate, how does that change the other sides? So we'll look at that today. We're going to start with something called Pythagorean related rates. And we're going to come up with like a goal for what we're going to do when we have these geometrical related rates. And we're going to first start by drawing a labeled picture of the situation. Let's get into our first situation. A 10-meter ladder is against a wall. Its bottom is pulled away from the wall at a constant rate of 0.5 meters per second. Determine each of the following, and we'll determine that in a second. But let's start by drawing a picture of the situation. So there is a ladder leaning against a wall. And that ladder is 10 meters long. Now we will label any constants, things that aren't changing. This ladder has a length of 10 meters. And that won't be changing. As it slides down the wall, the length of this ladder can't change. Okay, but presumably there's a floor here. And it says its bottom is pulled away from the wall at a constant rate of 0.5 meters per second. Now, this is a rate. So this is like, it's how something is changing. Well, what length is changing if I pull this away from the wall? Hopefully we can see that the length that is changing is the length between the wall and the bottom of the ladder. Whenever we have a horizontal distance, we often label this x. Now, x is a variable, not a constant, because as we pull this away from the wall, x will be changing. In fact, it tells us what the rate it's changing is. This is dx dt. How x is changing every second is going to be constant. It's going to be 0.5 meters per second. Okay. Now, the question is this a constant or is it a variable? Will this length, the vertical length, be changing or will it be constant? Well, I hope we can see that as the bottom is pulled away from the wall, the top has to be sliding down the wall, right? Like the ladder is not going to get longer, and so it'll slide down the wall. That's just like how something works. I wish I had a classroom so I could actually show you, like, if you pull it away from the wall, the top goes down. Okay, so this will be a variable. Call this y. What are some other things that might be changing? Well, this angle might be changing. I could ask about that. This angle might be changing. This angle is a constant. It's not going to change because the wall isn't moving. But these angles are changing. So those are some things that might be changing. Let's look at what the question asks. How fast is the ladder top? So here's the top of the ladder sliding when it reaches 6 meters up the wall. So it's saying, okay, we're pulling this bottom away. When this ladder top reaches 6 meters, how fast is the ladder top sliding? So how fast is the ladder top sliding? This is rate. It's going to be the speed that the ladder is sliding is the same as the change from the bottom to the top. How fast is this distance changing is the same as asking how the ladder top is sliding. So this is asking us for dy dt. Now, in related rates problems, I always recommend starting with what are the rates and then what are the variables that go with them. So they told us dx dt was 0.5. That's how this was changing. And that's going to tell us how this distance is changing. And so the variable that goes with it is x. And this x is the distance between the wall and the base of the ladder. What we're looking for is dy dt, and that's also a rate in this problem. So dy dt, how fast is the ladder top sliding? And that's a measurement of how y is changing. And so let's remember from last class that what we want to do is if we know what rates we need to deal with, we need to get an equation that relates x and y with each other. We need to get some sort of a relationship between x and y so that when we do the derivative with respect to t, we'll get dx dt and dy dt, and we'll be able to find what dy dt is. So we need a relationship between x and y. What is the relationship between x and y? Hopefully we recognize that this is a right triangle. And we'll have a lot of situations where we have a right triangle. And when we have a right triangle, we know that you can use the Pythagorean theorem that says a squared plus b squared equals c squared. Now here, I'm going to put 100. 10 squared is 100. This is a constant. I want to compare that to right here. It said when the ladder top reaches 6 meters up the wall. I cannot plug in 6 for y right here because 6 is not a constant in this problem. Y is changing. And so y is not a constant. When I do the derivative of y, it won't be 0. Y is changing. But if I plugged in a 6 right here, it would make it look like when I did the derivative that that y was a constant and the derivative would be 0, and that wouldn't be right. Okay, so once we have our relationship between x and y, we are going to do dt, the derivative with respect to time, because then I can see how the x is changing, dx dt, and how y is changing, dy dt. So what is the derivative with respect to time here? Well, the derivative of x squared is 2x times dx dt, because we did the derivative with a variable that isn't the same variable there. The derivative of y squared is 2y dy dt, again, because we're doing the derivative with respect to time. So we need to do the chain rule. We do the power rule, 2y dy dt, and the derivative of 100 is 0. Hopefully we can see why it's important that, like, this isn't, we didn't call this like c or something because it's a constant. So we want to plug in values for constants and we want to put in variables for variables, and so we need to be able to tell the difference. So now we should be able to answer this. We're looking for dy dt, okay? So that's what we're looking for. We're going to solve for this in a second. How fast is the ladder top sliding when it reaches 6 meters up the wall? So this distance, y at this point in time is 6 meters up the wall. dx dt, it said, was a constant rate of 0.5. But it didn't tell us what x is. It told us what y was, what dy dt was, and dx, or we're looking for dy dt, and it told us what dx dt is, but we didn't we weren't told what x is. And this will happen a lot in these related rate problems where they'll give us a bunch of things, but we need to know everything except for the one we're looking for. So we need to know what x is. How do we get it? Well, we have a relationship between x and y. And so we're going to go back in, and we're going to take x and y, and we're going to plug in for y now. Now, we couldn't plug in y when we were taking the derivative, but we can plug in y to solve for x. Because what this is saying, I'm subtracting 36 on both sides. I'm not going to put plus or minus here because this length is always going to be a positive, so x won't ever be a negative length. When I do the square root on both sides, usually I would put plus or minus, but when I know that it has to be positive, I'm not going to mess around with that. So x must be 8, because when y is 6, x is 8. That's what this tells us. So when x is 6, when y is 6, x is 8. And so I get 16 times 0.5 plus 12 dy dt equals 0, and I can solve for dy dt. This is 8, and I'm going to move 8 to the other side. Negative 8/12 is dy dt. And that can be simplified. Dy dt is negative 2. I'm going to divide by 4 and divide by 4. Negative 2/3. And I'm going to put units here. Y is being measured in meters, because if this is in meters, this is in meters, then when you do the Pythagorean theorem, this is also in meters. So y is in meters, and time is being measured in 0.5 meters per second. So meters per second. So there we go. So this is saying that if x is being pulled away at half a meter per second, the y is falling down at 2/3 of a meter per second. And the fact that it's negative tells you that the y is going down, which makes sense. Okay. Now the question is, this is being pulled away at a constant rate. I want you to make a prediction. Do you think that the y will be falling down at a constant rate also? If this is being pulled away at a constant rate, will this be changing at a constant rate? Yes or no? And we can find out. Let's see, what about when the ladder was a different height along the wall? What about when the ladder was like 8 meters instead of 6 meters? So that ladder's still being pulled away at a constant rate, and it's still falling down. The question is like, well, is this speed changing at a different rate at a different point on the wall? So I want you to do this on your own. Do this whole setup here on your own and try to find what is dy dt when y is 8. And this setup won't change. We still need a relationship between x and y. We still need x squared plus y squared equals 100. The derivative will still be 2x dx dt plus 2y dy dt equals 0 when I do the derivative with respect to time there. What has changed now is that y is 8. So y is going to be 8. And when y is 8, that will also change what x is. So x squared plus 8 squared equals 100. So x, this is going to be 36. So 36, x is 6. So when y is 8, x is 6. You should have gotten that. And so when I plug in, I'll get 2 times x is now 6. Dx dt is 0.5. Plus 2 times 8, because y is now 8. I'm just plugging in 8 for y instead. Dy dt equals 0. So this is 12. Half of 12 is 6. Plus 16 dy dt equals 0. I need to solve for dy dt, so I'm going to move the 6 over to the other side and divide by 16. So dy dt equals negative 6/16, which is negative 3/8, which is not the same number. It's still meters per second, but this tells you that if you pull the bottom away at a constant rate, the ladder was changing at a slower rate. Negative 3/8 is slower than negative 2/3. It was going down more slowly near the top than it was at the bottom. And I will try, guys, if we were in class, I would be showing you a video right now of how it looks when you actually pull a ladder. Oh, there's not a good way to do this. What happens if you pull a ladder away at a constant rate? You can really see that the top doesn't move at a constant rate at all. And I'll try to put in that video for you guys in a second. I'm not sure if I'll be able to. How about if the ladder is 1 meter up a wall? What if it's only 1 meter up the wall? What about when the ladder is like here? Well, so now like the ladder's being pulled away and the ladder's only 1 meter up the wall. How fast is it coming down? So this was negative 3/8. let's see how it is here. And again, I'll let you try this on your own. I hope you realize that we're going to do the same thing. We're going to take the derivative, get the same derivative, but now y is 1. So y is 1. So we need to solve for x. So we get x squared plus 1 squared equals 10 squared. X is 99, and so x equals square root of 99. And so when I plug in, I'll get 2 square root of 99 times 0.5 plus 2 times 1 dy dt. So y is 1 and x is 0.99 equals 0. And I can solve here. This will be negative square root of 99 over 2. And this is like, this is really close to 100. So this is going to be like negative 9 point something divided by 2. It's going to be negative 4 point something. It's moving way faster than it was up here. This is like, it's going way faster. And I hope I'm able to show you this video. We'll see. So as the ladder is getting closer to the ground, the rate of change of the top of the ladder is increasing. It's going faster and faster and faster the closer the ladder top gets to the ground. So the ladder top moves faster, even though the base is pulled out at a constant rate, which is maybe counterintuitive. The ladder top is moving faster, even though the base is being pulled out at a constant rate. Let's look at another Pythagorean setup here. You're going to be looking out for Pythagorean setups whenever you have like a horizontal distance and a vertical distance, and maybe like some distance between them. So in this case, the ladder was the distance between the wall and the floor. Sometimes this will change, and one of these will stay constant. Sometimes all three will change, and that's okay too. We just need more information. So let's look at this. A boat winch on a dock is reeling in a rope at a rate of 2 feet per second. You might not know what a boat winch is. A dock is where boats land. It's where like boats come in. Reeling in a rope means you're like making the rope get shorter and shorter and shorter. You're like, usually there's like a spinner with a handle that you're like pulling it in. Okay, so, and a boat winch is actually like a thing that you like turn to pull in the boat. So let's draw a picture of what's going on here. You may not be able to do this. The rope is attached to a boat in the water that has an altitude 5 feet lower than the winch. So there's like a boat dock, right? And there's a winch on this boat. It's got like a crank. And attached to that winch is going to be a rope. And the boat is 5 feet lower than the winch. So like, okay, so the winch is up high somewhere. The boat is being reeled in. Okay, that means, so this is a boat. I don't know if you guys can tell that. Okay, so here's my boat. And the boat is floating in the water, and it will continue to float in the water. It doesn't actually get pulled into the air. What happens here is that we've got a winch that's up higher than the boat. And as you pull it in, the boat will be pulled closer to shore. Okay, so let's think about what are the constants and what are the variables here. I hope we can see that because the boat will stay in the water, this height won't change as it gets pulled in, and it will form a right angle with the right under the winch. This boat winch isn't moving. This is a constant. That's important. This distance, the rope, this is the rope, right? And the rope is being reeled in. And so this length is changing. This is a variable, and I'm going to call, since it's the hypotenuse of the triangle, I'm going to call it C. And this is a horizontal distance, so I'm going to call it X. Okay. We usually use C for hypotenuse. You can use H for it if you really prefer. So let's see what it actually gave me. It said the boat winch is reeling in a rope at a rate of 2 feet per second. So what's actually changing? Well, this length of the rope is changing. It's reeling it in at a length of 2 feet per second. So dc dt is I'm going to make a mistake here on purpose. So 2 feet per second. So they're telling me that dc dt is 2 feet per second. Well, that's not quite right because c is this distance, and as it gets reeled in, it's getting shorter. And so dc dt must be negative because c is actually going down. Like this length is decreasing as the boat gets reeled in. So what variable goes with that? Well, c is a variable. And the other variables in this problem might be like this angle or x. In this case, what does it actually ask? How fast is the boat moving? Well, the boat is moving along the water. And so how fast the boat is moving is how fast this distance is changing. So it's asking me for dx dt. This distance, how much is this distance changing at any second? Well, that's how fast the boat is moving because the boat is moving towards the dock. And so the variable that goes with that is x. What is an appropriate relationship between x and c? Because that's how these related rates always work. If I'm looking for dx dt, I need a relationship between x and c so I can do the derivative to get dx dt. So what's the relationship between x and c? And I hope we feel good that the relationship must be that x squared plus 5 squared equals c squared. A squared plus b squared equals c squared. The two smaller lengths squared add up to be the hypotenuse squared. We should be pretty comfortable with the Pythagorean theorem from geometry, I hope. And this is a constant. 5 squared is just 25. I'm not going to rewrite it. I'm just going to go ahead and do the derivative with respect to time, because the derivative with respect to time will give me dx dt and dc dt, which I have. So d dt gives me what? Well, 2x dx dt. This will be 0 because it's a constant. The derivative of 25 is just 0, equals 2c dc dt. And it says, how fast is the boat moving when the rope is 45 feet long? What variable is that? Well, that's c. That's when c equals 45. And I was not allowed to plug in 45 here before I did the derivative because that would make it look like it's a constant. So when I did the derivative, it would come out looking like the rope wasn't changing, but that's not true. The rope is definitely changing. So let's look. What can I plug in? What am I looking for? How fast is the boat moving? That's dx dt. This is what I'm going to solve for. I know c is 45. I know dc dt is -2. It didn't tell me what x was, though. And so what do I need to do to find what x is? Well, hopefully we feel good that I'm just going to plug in c is 45 into here to solve for x. So x squared equals, I'm going to use a calculator here. I think 45 squared is like 2025 or something like that. I'm not sure. That might not be right. 45 squared is 2025. Okay, great. So 2025 minus the 25 we had over here. And x squared equals 2,000. And so x is the square root of 2,000, which is the square root of 20, which is, I don't know, I'm just going to do square root of 2,000 here. We're going to call it square root of 2,000. This could be simplified. It's like 20 times square root of 5 or something like that. I don't know. Let me see. Is that right? I think that's right. Square root of 2,000 is the same as 20 square root of 5. Yeah. Okay. So those are the same. Whatever. Okay. So x is whatever. I'm going to leave it as square root of 2,000 for now. And I'm going to plug that in here. Square root of 2,000. And so dx dt is going to equal 2 times 45 is 90. 90 times -2 is -180 divided by 2 square root of 2,000. And that can be simplified, but whatever. It's just going to be like some weird number. So -2,000, oh no, -180 divided by, this would be on this would be on the calculator section. And it gives me -2.012. We go to 3 decimal places in, oh, you guys can't see that? Oh no. I plugged this into my calculator and it gave me this. We go to 3 decimal places, and you never round in the middle of a problem. You just you'll notice that in my calculator, I was keeping these exact numbers throughout. I also could have done it as I could have done 2 times this, but I would go and select that whole thing. And then I could do -180 divided by this number, but I would go select this. I would not round in the middle of the problem to get negative 2.102. And then at the end, I round to 3 decimal places. That's what it wants on the AP exam. So why don't you guys try this on your own? How fast is the boat going to be moving when the rope is only 22 feet long instead of 45 feet long? We might think, again, that as you reel something in at a constant rate, that this distance would change at a constant rate. And that isn't the case, as we'll find out in a second. And I hope we can see the practical implications for this. Like, if you're engineering and you're building something, you need to know how the speeds are going to be changing at different points. Okay, so how about when the rope is 22 feet long instead? Well, all of this is still the same. This derivative is still the same. The only difference is now we're going to be plugging in 22 here instead of 45. And if C is 22, then X will change also. So at the place where this is 22, the X will be shorter also. So let's do that. Let's see what that is. X squared plus 25 equals, what is 22 squared? It's like 484 or something. I don't know. 22 squared. 484, good. So 484. So I'm plugging in 22 here to find what X is. So X squared is 459, and so X is the square root of 459. And so when I plug that in, I get 2 square root of 459 equals 2 times 22 times negative 2 is negative 88. And I can divide this and get oh wait, hold on. This was supposed to say dx dt. So dx dt, when I divide, the 2 will divide into this and get negative 44 over square root of 459. I can leave it like that, or I can actually find like the decimal. Let's go ahead and do that. So negative 44 over square root of 459. And now it's slightly different. Not a ton different, but the boat is moving slightly faster. So negative 2.054. And when you see these two numbers, you might think, oh, that's basically the same speed, but like it will change near the ends. So like when the rope is really long, that might be a big difference. Or when the rope is really short, like this will change dramatically. And you can try that if you want. You can try it like, well, what if it's only like a 7-foot rope or something? Like, how will that change? All right, guys, let's move on to a different type of related rate. In this case, the radius of a circle is increasing at the rate of 2 inches per second. So here we have a circle. Let's draw a picture. And the radius, which is this is the radius, is increasing at a rate of 2 inches per second. I hope we can see that this is a rate. And so how will we write this? Well, this is dr dt. Okay. So let's look at the question and set up our rates and variables. So at what rate is the area increasing? What rate is the area increasing? How do we write that in math? Hopefully we're feeling comfortable that this is dA dt. So our rates are about r, dr dt, and dA dt. dr dt is 2, and dA dt is what we're looking for. And I guess I should say inches per second. And so what are the variables that need to go with that I need to set up an equation between? Well, r and a. So I need a relationship between the area of a circle and the radius of a circle. And this is one you need to know. I found in the past that a lot of kids in calculus don't necessarily know the geometry formulas they're supposed to know. So if you don't know this, fine. This is a great time to learn it. The area of a circle is pi r squared. That does need to be memorized. I hope you already knew it. This is the relationship between the area and the radius of a circle. And I need that relationship between the area and the radius so that I can find the relationship between how they change, the way that their rates are related to each other. So of course, I'm going to do what? Well, we do d dt on both sides, and we get dA dt equals, pi is a constant, it's a constant multiplier, so pi times 2r, but r is not a constant, and it's with respect to t, so 2r dr dt. Hopefully you guys are feeling okay with this. Now let's see what we can plug in. We can plug in at what rate is the area increasing, so dA dt is what we're looking for, when the radius is 8 inches, given that dr dt is always 2. So it's just going to be pi times 2 times 8 times 2. Let's multiply 2 times 8 is 16. 16 times 2 is 32. dA dt is 32 pi. We usually put 32 in front of pi, not after. 32 pi. And what are the units here? Well, the RDT was in inches per second. Area is always going to be measured in square units, so inches squared per second. And we can kind of see that if we look at the units, what units here multiplied. R was 8 inches. And so if we do inches times inches per second, because it was R, which was inches, times 2 inches per second, you can see how the inches times the inches gives you inches squared. But you also can just know that area is always in units squared per second. Okay, I want you to try this next one on your own. This will be a different relationship, so it will be not necessarily the same variables and rates. At what rate is the diameter increasing when the radius is 4 inches? Indicate units of measure. So hopefully you're able to get it, but if not, let's try to work on it now, and you can go back and try this on your own later. Let's look at our rates. They gave us, real quick, if there is a problem with parts, the top of the problem goes with all 3 parts. The individual parts aren't necessarily used with each other. Sometimes they are, but the top information will always be for all 3 of the parts. Like if there's a number 3 part A, B, or C, any information in this will be necessary for A, B, and C. Okay, so at what rate is the diameter increasing? I hope we recognize this is d dt, the change in diameter with time. And that's what we're looking for. And we know that the radius is changing, so dr dt is 2 inches per second. And so we need a relationship between the diameter and the radius. So this is variables and rates. So what is the relationship between the diameter and the radius? Well, the diameter is the distance from one end to the other, and we should know from geometry that the diameter is 2 times the radius. Okay, so when we do ddt, the derivative with respect to time, the derivative of the diameter is dt. Here's a constant multiplier. The derivative of r is dr dt. So dt is 2 dr dt. Dr dt is 2, and so we get dt equals 2 times 2, which is 4. Diameter is a length, and so it will also just be measured in inches. So the diameter is measured in inches. This will be inches per second. Notice we didn't even have to plug in that the radius was 4 inches because there was nowhere to plug in the radius, and that's okay. We give some additional information we didn't need. So we got, when we are looking for dA dt, we need a relationship between A and the rate that we have. When we're looking for dd dt, we need a relationship between D and the rate that we have. So at what rate is the area of the circle increasing when the circumference is 10 pi inches? So at what rate is the area of the circle increasing? So here's our rate, dA dt. I hope we're able to find, I want you guys to be able to solve these on your own. So dA dt, and we have dr dt. So we need a relationship between A and R. So what is the area of a circle? Well, the area is pi r squared. Notice it also mentions circumference, but this is not a rate. So when I'm doing the ddt, I don't want to have anything to do with circumference here. I just want to have A and R, so that when I do the derivative with respect to time, I get dA dt equals, pi is a constant. The derivative of r is, I'm going to move the 2 in front. So 2 pi r dr dt. So the derivative of r squared was 2r dr dt. Because of the chain rule, I moved the 2 to the front because it usually goes in front of pi. So I'm just going to do that. Now let's see. So dA dt equals this, and that's what I'm looking for is dA dt. I know that dr dt is 2, but it didn't give me r here. It said when the circumference is 10 pi inches. Now I need r. This is a relationship between the circumference. This tells me a value of the circumference. And so now I do need to use the circumference here. Circumference equals 2 pi r. And what I'm going to do is plug in 10 pi here. I'm not taking the derivative, I'm just finding what r is. So I need to know what r is. It told me what the circumference was, and so I can use the relationship between the circumference and the radius. This is another one you should know, I hope. And so I can divide by 2 pi, and the pi's will cancel out. 10 divided by 2 is 5. So this is like saying when r is 5. So saying when the circumference is 10 pi inches is the same as saying when the radius is 5 inches, because we can plug in 5 for r to get that the circumference is 10 pi. So, they gave us the wrong variable. You will set up your equation that you do the derivative of with the relationship between a and r, because they give us dA dt and dr dt. But sometimes you'll need to use a different formula to find out what r is there. That's okay. So let's multiply this. 2 pi times 5 times 2 is 20 pi. So this is dA dt. So what should the units be for dA dt? Well, I hope we recognize that this is area. And so it'll be inches squared per second. So inches squared per second. Okay, an inflating balloon. So now air is being pumped into a spherical balloon. When you blow up a balloon, what's happening? Well, the balloon's getting larger, right? Okay. It's being pumped in at a rate of 4.5 cubic inches per minute. What rate is this? Well, if you couldn't tell by the fact that it's air being pumped in, that's a volume, I hope the units were a tip-off for you. Cubic inches per minute. So inches cubed per minute is dV dt. It's how is the volume changing, okay? And it's asking us to find the rate of change of the radius. So this is dr dt. So we need a relationship. So our variables and our rates. What are our rates? Well, they gave us dV dt. That's 4.5 inches cubed per minute. And dr dt is what we're looking for. So we need a relationship between V and R. And hey, look, they were really nice here. I will tell you the AP exam is not consistent on this. Sometimes they will give you, if they think oh, this problem is too hard as it is, we don't additionally want to measure whether they know their geometry formulas, sometimes they will give you a geometry formula. Sometimes they expect you to know this. So I'll give you a list at the end of this video of the geometry formulas you should already have memorized. And sometimes they'll give you the harder ones, and sometimes they won't. They will never give you area equals pi r squared. They will never give you area circumference equals 2 pi r. They will never give you the diameter is 2 times the radius. They won't give you those. But sometimes they will give you the relationship between for the volume of a cube. Now notice, this is already a relationship between V and R. So we're ready to go. They gave it to us. You should know this one, and you should have been able to come up with this even if they didn't give it to you. But if not, here it is. So what do we do? Go ahead and solve this one on your own. Well, you're going to do d dt so that we can find dr dt. So d dt, the derivative of volume is dV dt, which we know. 4/3 pi is all a constant. These are just numbers. Pi is 3.14. These are just a constant multiplier. So it's 4/3 pi times the derivative of r cubed is 3r squared times dr dt. And now let's see if we can plug it in. So find the rate of change of the radius. This is what we're looking for. When the radius is 2 inches, so we can put in 2 for r. And we knew that dV dt was 4.5. This will be, so 4.5 equals, multiplying by 3 and dividing by 3 will cancel out. And so we get 4 pi times 2 squared. 2 squared is 4, 2 times 2 is 4, and 4 times 4 is 16, so 16 pi. And so dr dt is 4.5 over 16 pi. Now, guys, I gotta tell you, I see on tests and quizzes a lot, kids will mess this up if they try to convert it to a decimal. They'll be like this, 4.5 divided by 16 pi. And this will give them the wrong answer. This is not correct. And I hope you can tell what is wrong here. What isn't right about how I entered this into the parentheses? Well, what your calculator is doing is it's dividing and then multiplying by pi. It's doing 4.5 divided by 16, and then it's taking that answer and multiplying times pi. But that's not what's supposed to be happening. This is not 4.5 over 16 times pi, these aren't the same thing. When you have something that's dividing, you really want the entire denominator to be in parentheses. So divided by 16 pi, and you'll notice this will give us a different answer, which is the right answer. I could leave it like this. This is completely correct. Or I could round to 3 decimal places. So 0.0. When I round the 5 up, it will go to 9. And we should put units. So if the volume was being measured in inches cubed per minute, the radius is a distance, it is just a length, should be in inches per minute. So volume is in inches cubed, area is in inches squared, and distances like a radius is just in inches per minute. Okay, guys, let's do 2 more. The Pillsbury Doughboy has decided to bake cookies for the calculus classes. He begins with 40 pi centimeters cubed of cookie dough. What is this? This is a volume. There is no rate here. It's not centimeters cubed per minute, but these centimeters cubed tell me it's a volume. It's an amount of dough. And that should make sense. Like how much dough you have is an amount. He rolls the dough into a cylindrical shape. He notices that the rate of change of the radius of the cylinder, so as he's rolling it out, the radius is getting smaller. It's decreasing at 0.5 centimeters per minute. So let's look at variables and rates. This is a rate, 0.5 centimeters per minute. What is this? This is the radius is decreasing at. So this is a rate. So the dr dt is negative 0.5, and it's negative because it's decreasing centimeters per minute. So I know I'll need an r in the equation. At the instant when the radius of the cylinder is 2 centimeters, determine the rate of change of the height of the cylinder. So that's dh dt, and that is what we're looking for. So I need a relationship between the height and the radius of a cylinder, and hopefully you know some formula with cylinder. And this also had volume in it, but volume is not a rate we have. There is no volume here, and so I cannot have a variable that's volume. But, they gave us some volume, so that at least is a hint that volume is involved. And I hope we know this formula. They didn't give it to us this time. It's something maybe you were supposed to know. The volume of a cylinder is just the area of the circle times the height. So it's the volume of cylinder is pi r squared. It's the area of the circle at the end times the height. Now, the problem is if I take the derivative right now, this would be a product rule, and I would get dr dt, dh dt, and dv dt, but there's no dv dt in this problem, and so there's something that I need to notice. V here is a constant, and the reason V is a constant is because as you roll out the cookie dough, are you changing how much cookie dough there is? No. As you roll it, the cookie dough will be a constant 40 pi. And so I need to recognize that the volume wasn't in here. And so I need to think to myself, is this a constant? And the answer is, yeah, the volume isn't changing even as you roll it. The shape is changing, but how much is there isn't changing. And so now when I do the derivative, I won't get dv dt. I had to plug this in first to recognize, I had to set up my rates to realize that this is a constant. Okay, and so I plugged it in before I do the derivative. Just like on the front, I plugged in, before I did the derivative, I was plugging in 100 because this distance wasn't changing. The ladder was always going to be the same length. In this boat one, this height was always the same. So we plug in constants ahead of time. We don't plug in variable values. So even though it says when the radius is 2 centimeters, I do not plug in 2 here right now because that would make the derivative 0, and that's not right. So, okay, do the derivative of both sides. Hopefully we get 0 equals. This is a product of 2 functions. The derivative of pi r, so we have to do the product rule. The derivative of the first one, well, this is a constant multiplier. So the derivative of pi times 2r dr dt. So this is the derivative of the first times the second left alone, plus we need to leave the first one alone, so pi r squared times the derivative of the second, which is dh dt. And now I've got a relationship between dr dt and dh dt, and that's all. So dr dt is negative 0.5, or sorry, negative 0.5 when r is 2. Now h we don't have, but r is 2 here, and dh dt is what we're looking for. So we need to find what h is. So how do we do that? Well, hopefully we feel good. We go back in and we plug back in for r here so we can find what h is. So 40 pi equals pi times 2 squared when r is 2. We can find what h is. We can divide by, this is 4, so 4 pi. H is going to be 10. So h is 10. And so now we can solve for dh dt. So pi, so 0 equals pi times 2 times 2 is 4 times dr dt was negative 0.5, h was 10, plus 2 squared is 4, so 4 pi dh dt. So I'm going to move this to the other side. Let's multiply some things out. Pi won't multiply with these, but 4 times 10 is 40. Half of 40 is 20, so negative 20 pi. So this is negative 20 pi. And when I add it to the other side, it'll be positive 20 pi divided by 4 pi equals dh dt. So dh dt is 5. What are the units? Centimeters. H is a length, so it'll just be centimeters per minute. Okay, last one, guys. Man, this is a long lesson. Ladder, 25 feet long, is leaning against the wall of the house. Ooh, just like that first one. The ladder is leaning against the wall of the house. The base of the ladder is pulled away, ooh, just like in that first one, from the wall at a constant rate of 2 feet per second. And this is a variable that's changing. This is x, and so this is dx dt. Consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. The ladder is 25 feet long. This is not a variable. Even as you pull it away, the ladder will stay the same length. This is a variable, and so you need to have it labeled. Try this on your own. Find what is the rate that the area of the triangle is changing. So let's see. The area of the triangle, this is dA dt. And so I need a relationship between x and, oh wait, hold on. What is changing? I have dx dt. Let me put my rates. I have dx dt. I need dA dt. So I need x and area, but there's no y. Notice there's no y here. So let's look. How do we find the area of a triangle? Well, the area is 1/2 the base times the height, right? So 1/2 the base times the height. That's how you find the area of a triangle. But notice here, there is no dy dt. And so if I did the derivative right now, I would end up with a dx dt and a dy dt. But there is no rate for dy dt. And so I never want to have a variable that I don't have a rate for. So I'm going to need to substitute this. So I'm going to substitute. And the way I'm going to substitute is I need a relationship between just x and y. And that's what we did before. We said x squared plus y squared equals 25 squared. And I can substitute by solving for y. Y squared is, I think this is, what did we say it was, 2025? Minus, that's not right. 25 squared is 625. 625 minus x squared, and I can take the square root of both sides. And this is what y is equal to in terms of x. And I can rewrite this as 1/2 x times the square root of 625 minus x squared. And now notice that I have an equation just between x and a. So I noticed, I know the formula for the area is 1/2 the base times the height, but the height is a variable. It is not a constant. This is definitely changing. As you pull this away, this height is going down. And so if you end up with a variable that you don't have a rate for, you want to try to substitute it out either as a constant. We saw that in the last problem. This variable we didn't have a rate for, so we said, oh, was it a constant? Yes. This time y is definitely not a constant, so we can't just plug it in. And so instead we found a relationship between x and y and substituted in what y was equal to. So dA dt equals, this is a product. I will have to do the product rule. The derivative of the first one is 1/2 dx dt times square root of 625 minus x squared, plus, I leave the first one alone, times, this is so ugly. Guys, this is a power rule with a chain rule kind of thing going on. This is 625 minus x squared to the 1/2 power. So it's going to be 1/2 times 625 minus x squared to the negative 1/2 power times the derivative of the inside. The derivative of negative x squared is negative 2x times the derivative of x is dx dt, because we were doing it with respect to t here. So be a little careful there. So this is going to, so this whole thing is the derivative of this. 1/2 times 2 will go away. And so this will be times negative x dx dt over the square root of 625 minus x squared. It's dividing because it's a negative exponent. And so let's see. When the base of the ladder is 7 feet away from the wall, so I can plug this in. So dA dt equals 1/2. The ladder was being, dx dt was 2. So 1/2 of 2 is just 1, times the square root of 625 minus 7 squared is 49, plus x is 7, negative 7 times dx dt was 2, over the square root of 625 minus 7 squared. And I actually think this comes out pretty nicely. I think this is, I think 625 minus 49 is a perfect square. Let me look. 625 minus 49, square root of that, I believe it's 24. Oh no, what did I do? Oh, I didn't put of that answer. 24, okay. So this is 24 plus 1/2 of 2 cancels out. It's negative 49 over 24, whatever this comes out to be. So equals. Great. Guys, these rates, I want to just make sure we have the big idea understanding. If you have a relationship between rates, so rate 1 equals rate 2, we want to like find some relationship between these. They're not equal, they're related to each other in some way. Then what we do is we find the relationship between the variables and we do d dt so that we end up getting a relationship between the rates. Today we saw how that worked with Pythagorean rates and some of the simple geometric rates. We'll do some more of this next class. I hope you're feeling good about it, and you'll hopefully feel even better once you practice some on your homework, guys. I think the homework is fairly important just because there wasn't a ton of independent practice today, and I want you guys to get that practice on your own tonight.